Hello. Okay, it's 8:20, so I'm going to get started. First, let's just acknowledge that, hey, it's Friday. This has been an exhausting week, and I recognize that, but we have a weekend. The sun is shining. Let's point out the things that are positive. I also want to thank everybody for turning in their lab reports. That's good job. I've just started to grade those, so stay tuned for getting your graded lab reports back. Okay. Today, being Friday, is a quiz day, so don't forget to set aside 2 hours in your schedule for today to take the quiz. And it will be the usual procedure and rules. It'll be on Blackboard. It'll be available starting at 9:30 our time this morning. Has to be turned in by 11:59 this evening, okay? Based on one of the homework problems for this week. Next week for 110C is a typical week, same pattern. Next homework will be due Monday evening. Next week is not typical for lab, right? Next week is the lab exam. So, remember I sent you a video a while ago now with information about that lab exam. As of about 6 this morning, there have been 10 views of that video. That means there's quite a few more people that need to watch that video. I urge you all to watch that video before you start the lab exam. It's going to tell you, in fact, well before you start the lab exam, because you do need to prepare. And it tells you how to prepare. And it tells you what the exam is going to be like procedure-wise. Okay, it's one of my usual videos, but I'm talking just about the lab exam. Now, in case you can't find that email in your inbox, I sent it probably about a week ago now, or close. I have uploaded a link to Blackboard in 110L, so you can find it there. Okay, but please do watch that. And then, as for next week, as I explained in that video, we're not going to be in the lab room. Everybody's working individually on the lab exam. Becomes available Monday morning. Once you open it, you'll have 8 hours, just like one of our midterms. Okay? You do your work, you produce one PDF file that you upload to Blackboard, just like an exam. It is an exam. It's an exam in 110L. Okay? The absolute latest that these can be turned in is 11:59 p.m. next Thursday. So there's a 4-day window when it's available, but you have 8 hours once you start. Okay? So I strongly, strongly, strongly urge that you watch that video so that you know you are prepared to take that exam once you click and open it. Okay? So no meeting in lab next week. You're working on the lab exam. Individually, remember. Okay? Okay. Does anyone want to ask a question about anything I've said? Okay. So, as for today's class, I'm bringing up the first learning objective that we want to talk about today. We're focusing on chapter 11, section 6, in which we're going to yet again write down another version of Newton's second law. Okay? And this will be a angular or rotational version of Newton's second law. Okay. It's the only learning objective in all of section 6 in chapter 11. Apply Newton's second law in angular form, i.e. rotational version, to relate the torque acting on a particle to the resulting rate of change of the particle's angular momentum. So the videos yesterday for Thursday's class introduced the concept of angular momentum of a particle. And I talked in some detail about how to calculate the angular momentum of a particle about a specified point. And it involved a vector product like torque does. Okay, so that was the 2 videos from yesterday. It's all about angular momentum. Today, we're going to build from there. And we're going to write down a new version of Newton's second law. So what I've done over here on the board is write down a couple of key points to go with this learning objective. The first one is a review point from chapter 9. Halfway through chapter 9, we wrote down a new version of Newton's second law for what's called the translational motion of a particle. Translational means just linear along a line, okay? And that new version of Newton's second law, the way Newton actually said it, by the way, in his great work, is that the net force on a particle equals the rate of change of its linear momentum. Okay, that's what Newton actually said, except he said it in Latin. Okay, now that's for the translational motion of a particle, but that's just another version of Newton's second law. All right, now what we're doing in this chapter is we're writing the rotational version of this. All right, so now we're going to talk about the rotational motion of a particle, but here you got to specify the point that you're watching it about as it moves. And then all you do is write the rotational version of this, where you replace each quantity up here with its rotational analog. So net force becomes net torque, because torque is the rotational analog of force. And linear momentum in the derivative here becomes this new quantity, angular momentum, and that's the symbol for it from yesterday's videos. Okay. So yet this new version of Newton's second law for the rotational motion of a particle says that the net torque on a particle equals the rate of change of that particle's angular momentum. Forces change linear momentum, torques change angular momentum. That's what Newton is telling us. Okay. All right, so what I want to do, first thing then, is do a Wiley Plus type of interactive exercise that involves torque and angular momentum. It's based on a pastime that some people enjoy, in which you take a pumpkin from the ground and construct some kind of device to hurl it vertically upward. And the goal is to construct a device that can hurl the pumpkin the highest. Okay, they call it pumpkin chunkin. And what you do, I'm going to show you an animation in which I will do the physicist version, in which the pumpkin is clearly just going to be treated as a particle, and it's going to be fired upward from the ground. We're going to say the pumpkin has some mass m. It's going to be projected upward from a coordinate on the x-axis that we're going to label x0, which means it's not necessarily fired from the origin. It's got an initial velocity v0 of v0 j hat, where v0 is some positive value, right? It's got to be projected up. And that's all. You just give a pumpkin an initial upward velocity. Well, after that, after you give it the upward velocity, it's really just a chapter 2 problem. Yes? Throw something up from the ground, watch it go up and then come back down. All we're doing is taking that chapter 2 scenario and talking about some new quantities that we didn't talk about in chapter 2, namely angular momentum and torque. So we're going to find the angular momentum of this particle, the pumpkin, as a function of time. It's going to be changing with time, okay? And with respect to the origin, you got to tell me what point you're calculating angular momentum about. Okay, we're going to express that angular momentum in unit vector notation. Then we're going to find the net torque on the particle with respect to the same point, the origin, and express that in unit vector notation. And then we're going to verify that the answers from A and B are consistent with this new form of Newton's second law we've just stated. Tau net equals dL dt. So let me show you the animation. You can see the physicist version of it. Let's see if I can move this around. Okay. This is the physicist picture in which we've taken away any extraneous information and focused on the important things. There's the particle, the pumpkin, at time 0. It's just going to be given its initial upward velocity. So it's going to have an upward linear momentum. In fact, that arrow drawn in kind of an orange color, if I hover over it, you can just barely see it, there we are, represents the linear momentum. That's supposed to be P arrow, but this web browser is having trouble with the arrow part of in there, okay? So that represents the linear momentum, P, of the pumpkin at time 0. That blue downward arrow is just F grav with an arrow on top, okay? The other blue arrow, it's kind of hard to see it, but it's pointing from O, the origin, out to where the particle is the position vector, R. And then all we do is run the animation. It's no great, there's not going to be any great shock. What's going to happen? It's going to travel up and slow, reach some highest point where at one instant it's at rest, and then speed up and come back down. So, but you'll be able to see these various vectors follow the particle, and some of them will change with time. Okay, up and down. And this symbol is R perpendicular, R perp. All right, so now let's go back and forth between the wording of the problem and the animation. And our first task in part A is to get a formula for the angular momentum of the pumpkin. Okay, so this example is about both angular momentum and torque. And part A says find the angular momentum vector for the pumpkin, okay, as a function of time. It's not going to be a constant. Now, to do that, let's draw our own sketch, okay? We've got the animation, and that helps. It helps us visualize what's going on. There's our coordinate system. Point O is important. That's the point we're calculating angular momentum about. Let's draw the pumpkin. Hey, I've got orange. Just at some moment, there it is, on its, let's say, upward journey. Okay, so that it's got, at that moment, a linear momentum, little p arrow, up. That would be something like roughly, oh, something like that. Okay. What else do we have? The position vector, R, arrow, points from point O to where the particle is. And there is, of course, during this motion, only one force, F grav, acting, and that would be down. Let me draw that like that. Those are some of the important vectors. And we'll extend that down a little bit. That'll be helpful. All right, so we have to find the angular momentum vector in unit vector notation. So what's the safe place to start? First of all, I think it's very helpful to draw a picture So the safe place to start, oops, I want black, is L equals R cross P. That's the definition of angular momentum for a particle. Vector product of the position vector, there it is in blue, the R, and the linear momentum vector, there it is in orange. It's vital to have a picture where those two vectors are drawn, even though it's clearly just one snapshot in time. Okay? Because we have to be clear what we have to deal with. We have to be dealing with that vector product. So we have to bring all we know about vector products to bear on this calculation. And we know quite a bit about vector products now, including a couple of ways to actually calculate vector product. I'm going to go through actually both of them for practice. Okay? One way to calculate a vector product is this is method number one, if you like. In method number one, there's basically two steps. Step one, use the canned formula for finding the magnitude of a vector product. And step two, get the direction from the right-hand rule. That's a method for finding a vector product. The second method is to go straight to the canned formula. It's a mile long, that it puts in all the various components of R and P in various places, and it puts everything in unit vector notation. It's long. It looks ugly and intimidating at first, but it's very handy if you know the components of R and P. And if you're wondering where that formula comes from, it's derived in chapter 3, section 3. I'm going to do both methods because I think we need practice to get used to this. Okay? Let's start with what I called there method one, which, remember, method one itself is a two-step process. First, find the magnitude of the vector product you're dealing with. In our case, and note my notation. It's very important to be clear in what you write and in your own mind what you're doing. We are finding the magnitude of L at the moment. Here, we have to make sure we have a good understanding of a vector product and how you deal with it. If I have a vector product of any two vectors, there's a canned formula for finding the magnitude of it. It goes like this. Take the magnitude of the first vector in the product, in our case that's R, scalar multiply that by the magnitude of the second vector in the product, in our case that's linear momentum, and then scalar multiply that by the sine, not cosine, of an angle called phi. What is phi? By definition, phi is the angle between R and P when they're drawn with a common tail. I have not put a phi anywhere in my drawing, have I? I'd better do it. The way I visualize it is I just, in this kind of a picture, I just imagine extending the line of R, and I can imagine just extending the R out along that line so that the tail of R is where the particle is. Then R and P have a common tail. And I think it's pretty straightforward then to see what the phi is. It's right there. Okay? The angle between R and P when they're drawn with a common tail. Okay? All right, that's the formula for finding the magnitude of a vector product. That's what you've got to start with. We have no leeway. That is what we must start with. Now, after we do that, we may very well have to scratch our heads and think about how to deal with that formula in this situation. And it does seem a little intimidating if you think about it carefully. For one thing, remember, the pumpkin's going up and then coming down. And that R arrow has to follow it from O to wherever the pumpkin is. So the R is going to be going up and then coming down. The R is changing. So the phi is changing, isn't it? It sounds like that's going to be pretty messy to deal with. Let me just show you the typical kind of approach. You know what would be a useful angle to deal with? Not that phi so much. but this one over here. But wait, that's the same, isn't it? Okay, phi. Ah, okay, if I do that, then notice something. For the magnitude of L, let me just do a little grouping here. Magnitude R sine phi times magnitude P. That's all right, right? This is all just scalar products there. Doesn't matter what order they're in for a scalar product. Look at magnitude R sine phi. Well, there's R. So that's the hypotenuse, do you notice here, of a right triangle. And magnitude R sine phi is this right along here, which is the perpendicular distance from O out to that line there. But that's just the x coordinate of that from there to there, yes? That's what the problem calls x0. See that slider up there? Lets me even adjust what x0 is in the animation. And you know what's good about noticing that? That I can write this as x0 times the magnitude of P. Even as the pumpkin goes up and it comes down, it's just going vertically up and coming vertically down, right? It's just going straight up and coming straight down. So that x0 isn't changing. Even though the R vector is changing, the x0, which is the x component of R, is not changing. That's then very helpful to notice that that's part of this expression. The other thing you could write here is x0 m times the magnitude of v, yes? Linear momentum is m times v. Now, we can't forget all the physics we've learned already. What should we do about that? That seems to be staring us in the face. The magnitude of the pumpkin's velocity. Problem doesn't tell me anything about what that is. But we have enough physics to know exactly how to get that, don't we? That's a chapter 2 problem. If I say there's some initial velocity v0 upwards, you can give me the formula for that v. Now, all I want right there is the magnitude of it. Okay? But the point is, it's just free fall. And we understand, yes, the physics of that already. So I'm not going to worry much at this moment about that. When time comes, I can have plenty to tell you about that v. What about the direction, though? Right? This first method of finding a vector product, very good, involves 2 steps, magnitude and direction. We just did the magnitude part. Let's just say we got an expression for the magnitude of L. The direction, right hand rule. Okay? Remember what we learned about that. First of all, whenever you take the vector product of 2 vectors, the resultant, in this case we're calling that L, is perpendicular to the plane containing the original 2 vectors. Our original 2 vectors, R and P, are in the XY plane. So L must be perpendicular to the XY plane, which leaves me only 2 options, yes? Perpendicular and towards you, or perpendicular and away from you. So out of the board or into the board. What would those directions be in terms of a coordinate axis? What is out of the board? What would you call that direction? I'll wait and see. Does anybody wish to answer?
Positive z.
Positive z, somebody says. Yes, positive z is out of the board. Negative z would be into the board. So L is either plus z or minus z. How do we figure out which of the two? The right-hand rule. So now I want everybody to do it, please. Try it for yourself in the privacy of your own mind. I ought to see right hands moving, if I can see you, and get a direction for R cross P, and then we'll compare. Remember, we only have to come to the conclusion about out of the board versus into the board. Those are the only two things we're worried about. Okay, did everybody try it? Does everybody have an answer in their head? All right, let's do it then. I like to use the 2-pen method myself. One pen represents R, the other pen in this case represents P. I start out with the pens more or less in the original configuration, but then I slide them so that they have a common tail. Blue is R, orange is P. Holding them with my left hand because I need my right hand for the right-hand rule. All right, then I extend the fingers of my right hand and the thumb, put the fingers along R with the palm facing P so that you can push R on top of P. And your thumb points in the direction of the cross product, which in this case is out of the board. Right? Plus Z. Is that what you said? Okay, now, we need to be careful though. That is drawn assuming the pumpkin is traveling upward, yes? Yes? So we better say plus Z when it's going upward. What about the downward trip? Well, clearly this picture changes in that the P vector now points down. What's the direction for R cross P then? Just think of this picture, but with the P arrow now down. Still can only be plus Z or minus Z. What direction do you get this time? You get minus Z, R, now P is this way. Slide them so they have a common tail, hold them with your left hand, then reach in with your fingers of your right hand and thumb extended, fingers along R, palm facing P, so that you can push R on top of P. Your thumb points into the board. So the direction is negative Z when it's going downward. That's going to be a little bit of a pain to deal with, isn't it? The direction of the L is going to discontinuously change. Well, I guess I should say continuously change from pointing plus Z to minus Z when it transitions from traveling up to traveling down. Well, that's what we get. Now let me show you a second version, which is the form I'm going to use. Okay. The second method for calculating L is to use that hideously long formula for any vector product. Now in this case, remember, now you're going to use the components of the two vectors you're crossing, in this case R and P. So it looks like this: Y times P sub Z minus Z times P sub Y, all times I hat, plus Z times P sub X minus X times P sub Z, all times J hat. Write this stuff very carefully. Plus X times P sub Y minus Y times P sub X, all times K hat. Write that very, very carefully. Being very careful about what's a subscript and what isn't. Okay, that's this canned formula for finding the vector product R cross P. Useful if you know the components of R and the components of P. Let me show you how to use that in this case. What usually happens, if there's any luck going in our way, is that a number quite a few, hopefully, many, hopefully, of those various terms go to zero. That would make life a lot better. Now, that's going to happen here. For one thing, the motion is entirely in the xy plane. So for the position vector r, there is no z component, right? And for the linear momentum p, which is only vertically up or vertically down, not only is there no z component, but there's also no x component. So the only component of p is p sub y. And there's no z component of anything in r and p. So now let's go right down the line, term by term, and put zeros for anything that's zero. The y coordinate of the pumpkin, not zero. But the z momentum of the pumpkin, definitely zero. The z coordinate of the pumpkin, zero. So that term's gone. Next, z coordinate of the pumpkin, zero. X coordinate of the pumpkin, not zero. But z momentum of the pumpkin, zero. So that term's zero. Told you this is going to be good. Next, x coordinate of the pumpkin, not zero. Y momentum of the pumpkin, not zero. Well, good. Something you can't have everything be zero. Y coordinate of the pumpkin, not zero. X momentum of the pumpkin, that's zero. So look at that. Out of all those terms, look at the only one that has survived, and it's for L arrow now, this expression. And write it down exactly the way you see. X times P sub Y times K hat. And that's what I'm going to use to give my answer for part A. Let me show you. First of all, I know what to put for the X coordinate of the pumpkin. It's this X0. And that's not changing as the pumpkin moves up and down. Right? That's not changing as the pumpkin moves up and down. What can I say about the Y component of the pumpkin's linear momentum? That would be m times the y component of its velocity. That's got to be true. Linear momentum is m times v, but I'm just talking about y component. Now I need chapter 2, folks. Chapter 2. What is the formula for the y velocity of an object in free fall? Because that's what's going to go there. Anybody have a suggestion? Let people think about that a minute. Gabriel? Ask a question. In terms of things that are stated in the problem, what is stated in the problem? V initial. That's it. Of course, you can always have little g. That's a hint. Anyone have a suggestion for what physics idea could we use to express that y velocity of the pumpkin? Talking about the whole story begins the minute, the instant, the pumpkin leaves whatever this firing mechanism is. And it has this initial velocity v0 upward. If I tell you, hey, I've thrown something upward from the ground with a velocity v0, and then I could ask you, tell me the velocity 2 seconds later. How would you do it?
We
Somebody's coming in. Yes.
will use the constant acceleration equation.
So we have a suggestion to use the constant acceleration equations. Free fall is constant acceleration motion. We have in general 3 of those. Everyone have a suggestion for which one to use? Yes, Luke.
V initial plus AT.
Yeah, first one. V initial plus AT. Isn't that an easy one? I know we've done so much difficult physics now that the simple stuff we did in chapter 2 is like, oh, I completely forgotten all that. Well, we do need to remember all of it. Okay. So constant acceleration equation number 1 says, to find the y velocity at any given time, take the initial y velocity plus AT, but A is negative G. So let's write this as V0 minus GT. See how I got that? Your book in Wiley Plus is not going to give you that. Your book in Wiley Plus is going to say, hey, you got to figure out how to get from there to there. But notice the y momentum depends on time. Well, of course it does, because the y velocity does. The pumpkin doesn't move with constant velocity. It's slowing on the way up, and it's speeding up on the way down. All of that is contained in that formula. So now all I have to do is put these symbols here and here into this formula, and I'll have the answer for the angular momentum of the pumpkin in unit vector notation. I'll have an m times an x0, and then in parentheses, v0 minus gt, and at the end, k hat. Boom, there's what you're supposed to find. The angular momentum of the pumpkin relative to the point O, as it depends on time. Note everything else in this formula is constant. Mass of the pumpkin is constant. This x0 coordinate is constant. V0 is just a number, a constant, and G is a constant. Everything's constant, but then there's a T. So if I were to make a plot of this part right here, by the way, this part, everything multiplying the k hat is what the physicist would call LZ, the Z component of the angular momentum. What if I plotted LZ versus time? What does it look like, such a graph? LZ versus T. Yeah, in fact, if there was a lot going on here, so you may not have noticed it first, but the animation gives a plot of it. LZ versus T. May be hard to read from a distance, but that's LZ in kilogram meter squared per second versus T in seconds. And yes, it's a straight line with a negative slope. Well, I can see that right from this. I mean, if you want to write this out, you can write it out like this. M x0 v0 minus M x0 gt, all times k hat. And we're plotting the thing in the parentheses versus t. And although the symbols might look a bit odd to you, you'd need to be able to recognize that this is just of the form b plus at, constant plus constant times t, i.e. the equation of a straight line, where b is the vertical intercept and a is the slope. So the vertical intercept is m times x initial times v initial. So to make this graph and this animation, apparently they assumed some value for m and v initial, and the slider shows you what the x initial is. And then the a, the slope, is negative m x initial g. Okay? And there's the negative. That's very clearly showing you you're going to have a negative slope. So the angular momentum, the z component of it, is a linear function of time, and when you plot it, it's got a negative slope. Now, what if I repeated the pumpkin challenge by firing the pumpkin not from x0 equals 1 meter, but I moved it out to x0 equals 2 meters. And then fired it upward with the same V initial. How would that graph right there be different? The LZ versus T plot. I'm changing one thing. I'm firing the pumpkin not there, but there. Straight up. So you're going to change both the vertical intercept and the slope, right? Which you can see right here, yes? The vertical intercept is this. It depends on the x0. You make the x0 bigger, the vertical intercept gets bigger. But the slope also depends on x0, doesn't it? And a bigger x0 is going to mean a bigger negative slope. So all I have to do is change this x0 slider and watch the LZ graph. Sure enough, larger vertical intercept, steeper negative slope. Okay. Everybody understand how we did this calculation? That's part A. All right. Part B. Let me do this by muting that temporarily. Turn that up so we have some board space. Let me tell you what part B asks us to do. I already read it to you, but I'll remind you. Part B says, find an expression for the gravitational torque. Right? Because there's an F grav acting vertically down. And so there it is over here to the side. So there's a torque on the pumpkin about 0.0 from F grav. Okay. So how are we going to do it? Well, let's do it by starting. This is a safe starting point. R cross F. In this case, F grav. This time, you know what I'm going to do? I'm going to go straight to the long formula for the vector product, like I did up here with the L. But now I'm doing it with torque. So it's R cross F, not R cross P. But let's write it out. Okay, so you start with Y times Fz minus Z times Fy times I hat plus Z times Fx minus X times F sub Z times J hat plus X times F sub Y minus Y times F sub X times K hat. R and F now. Now go down the line and see which quantities are zero. Again, the particle is in the XY plane, so it has no Z coordinate. And the force has only a Y component, right? So anywhere where there's a Z component or a Z coordinate, I put in 0. So I get 0 there, 0 there, 0 there, getting lots of zeros. Okay, X coordinate of the pumpkin, not 0. The Y force on the pumpkin, not 0. But there is no X force. Yes, gravity doesn't pull horizontally. So the only term that survives in the torque, gravitational torque, is X times F sub Y times K hat. Again, X is equal to the X initial value. As the pumpkin moves up and down, that's constant. And Fy means the Y component of the force that you're talking about. There's the force, of course, F grav. Note what you would put for the Y component of that force. Be careful. Negative mg. And to not put that there is Incorrect. So put those expressions in and you have a formula for the torque. You'll have negative m x initial g k hat. That wasn't too hard. And look at that. That's it. And look what else. You see any t's? No, right? It does not depend on time. The torque, the gravitational torque is constant. Even though the pumpkin moves upwards part of the time and downwards part of the time. Well, of course, because F grav doesn't change. Right? F grav is constant. Sure enough, the torque we get from it is constant. Okay? Let's at least double check the direction. See what it's telling me for the direction? It's hidden, it's here, it's encoded in the symbols. Negative k hat, negative z, i.e. into the board. You should be able to verify that with the right-hand rule. R cross F. You should be able to check that for yourself with the right-hand rule. The R and the F, not the P, the F. Slide the R out to there, take fingers of your right hand, palm facing F, push R on top of F, your thumb points into the board. Negative Z. Okay? So the torque is in the negative Z direction. In other words, everything multiplying the K hat is the Z component of the torque. So that's negative mx naught g. Constant. Notice something else. Look, negative mx naught g. Now look over here in the L formula. Negative mx naught g times t. Well, there's a close relationship there, isn't there? Okay. But let's double check real quick with the simulation, and then we'll have one more step, which won't take very long. Let me unmute so you can see. Now, you can't see it right now, but if I slide this down, you'll see there's a second plot of tau sub z, the z component of the torque versus time. And look, it's constant. All right, that's all I want you to see for that for right now. One more thing, won't take very long. We are to verify our new version, the rotational version of Newton's second law, tau net equals dl dt. We're going to verify by taking our answer from A and taking the derivative of it, dl dt. Because we have a formula for L in part A as a function of t. All right, there it is. It might look weird to you, but note, every symbol but the t is a constant. So we ought to be able to take that derivative. If all those symbols bother you, think of it in that form, b plus at, where the b and the a are constant. So what do you get when you do dl dt? Just think of it in this form for right now. What's the result of taking the derivative of this right here? A, right? It's the constant a. What is that in our case? Negative m x0 g. So negative m x0 g k hat. Now that's from part A, right? That has nothing to do with part B. That is solely from part A. In part A, I found L. It depends on time. In part C, I calculated the derivative, the rate of change of L. And notice that there's no t anymore. dl dt is constant. All I have to do, though, is compare this with the answer from part B. And I see that the answer for part B for the gravitational torque was negative mx0 gk, exactly what I got for dl dt. So what I've done is I've independently verified that dl dt is equal to the gravitational torque in this problem. Okay? So we have given you an example of how this equality, the situation where something's moving, we found L, it's a function of time, we did dl dt and got a result for that. We separately found the torque, and then we compared the torque with dl dt, and they were the same. Now there's still other stuff, as you know, Wiley Plus loves to do with these kinds of problems. There are things you could still do with this animation. Okay, you could leave it right like that. You could say something like, using the information from one or both of these graphs, find m, the mass of the pumpkin. Should be able to do that. Okay. And then maybe from the other graph, you could find, after you find m, you could find v initial. Because to make graphs with numbers, see numbers? There had to be a number they used for m, yes? And there had to be a number they used for v initial. They just didn't tell us. Well, we can figure it out anyways. Okay? All right, so that's the new version of Newton's second law. Tau equals dl dt. There is one more version of Newton's second law, which we're going to talk about on Monday. It's an extension of what I just said, tau equals dl dt, but for a system of particles. And it's going to lead to our third conservation law. We've had conservation of mechanical energy, conservation of linear momentum, and now there's going to be one more. So there'll be a video coming your way for Monday's class, and that's what we'll talk about on Monday. Okay? Okay. Have a good weekend.